Alright, so in this video, we're going to go over some practice problems on the material covered this week. So we're going to start with section 7.1 here. So looking at question 17, we want to evaluate this here. So what we have is minus the square root of 81. So when we evaluate this minus is going to still be out here since we have it on the outside of our radical. Now, we know that the square root of 81 is going to give us positive 9 here. So this evaluated is going to be negative 9, and we know that this is the case because 9 squared is going to give us 81, so this means the square root of 81 is 9. Let's look at another example here. In this case, we're looking at the third root, and we have this minus inside of our radical here. Now, since we're taking the third root, it's okay to have this minus in our radical, but whenever we're taking an even root here, if we have a minus inside of our radical, it will not be a real number. So just got to be careful of that. But in this case, evaluating this here, this will just be negative 4. And the reason being is because negative 4 cubed, which I'll write out in the expanded form here, is going to give us negative 64, since we have a negative times a negative, which gives us a positive times another negative. All right, let's look at these next two examples here. For question 30, we have the fourth root of negative 256. Now, like I said, we need to be careful when we have this negative inside of our radical here. And in this case, we're looking at an even root of this negative number here. So when we evaluate this, actually the answer here is going to be not a real number. And the reason is because any number raised to the fourth power would never be negative. And for this example here, we might think that, well, 4 to the fourth power is 256. But here we have a negative 256. So even negative 4 raised to the fourth power here would still give us a positive 256. So in this case here, our answer is just going to be that this is not a real number. All right, let's look at this next example here. We have the square root of this fraction now. Now, both 100 and 9 are perfect squares, so when we evaluate this answer here is just going to be 10 over 3, and this is because 10 over 3 raised to the second power here would give us 100 over 9. So that would be our answer for this one, 10 over 3. All right, so for the next two examples, we're going to be graphing these functions, and we also want to give its domain and range for each one. So for this first question here, we want to graph this function, f of x is equal to the square root of x plus 3. Well, when we're graphing these square root functions, the first thing that we actually want to do is identify the parent function in this case. So the parent function in this case is going to be the square root of x, and if we were to graph this, let's graph it in blue here, it would look something like this. This would be our square root function. So if we wanted to graph this guy, the square root of x plus 3, what this tells us here is that we're taking our parent function, the square root of x function, and we're moving it 3 units to the left. So let's graph this guy in green here. We're taking this parent function in blue and moving it 3 units to the left. We're going to have a point here, here. So just moving these guys 3 units over. So our function in green is going to look like this here. All right, and then we want to find the domain and range of this guy. Well, we know we can't take the square root, since this is an even root, of a negative number. So that means everything under this radical here needs to be greater than or equal to 0. So let's write this on the side here. X plus 3 must be greater than or equal to 0. If it's not, then this will not be a real number here. So that's the restriction on our domain in this case. So solving for x, we're just going to subtract 3 on both sides. So this tells us that x must be greater than or equal to negative 3. So our domain in this case, in interval notation, is going to be negative 3, and we're including that guy all the way up to infinity. So our input values can take any values in this interval here. Then our range, we can easily see from this graph here, this is going to be the range of all of our output values. So notice none of our output values are going to be negative. So our range in this case, in interval notation, is going to include a 0 all the way up to infinity. If we're looking at a square root function here, our output will never be negative in this case. All right, let's look at this next example here. We're going to do the same process for graphing this guy. We're first going to graph the parent function. Now in this case, our parent function is the third root of x. And so we'll graph this guy in blue again. And we can graph this guy just by plugging in points here, just like we did for this one here. If we were to plug in 0 for this, we would just get 0. So we have a point there at the origin. If I were to plug in 1 here, I would get 1. So we're going to have a point here. And if I were to plug in -1, I would get -1, and so on. A next point that would be good to use would be 8 here, because we know that 2 cubed will give us 8. So that means the third root of 8 will give us 2. And similarly, the third root of -8 will give us -2. So this is what our parent function looks like, the third root of x here. So then what we'll do is graph this guy in green here. Now what this is saying is that we're taking the third root of x and we're adding 1 to it. So what's happening is we're taking this parent function and we're moving 1 unit upwards. So all of these points here are going to move 1 unit upwards. So we're going to have a point here, here, and here, and then on this side, there, and there. So this is what our function in green here looks like. All right, now in this case, we want to find our domain and range. It doesn't matter if we have a negative number under our radical here, because we can take the third root of a negative number. So we don't have any restrictions on our domain in this case. We can also tell this by looking at the graph. So our domain is going to be all real numbers. And then similarly, we don't have any restriction on our range. So this guy will be all real numbers as well. All right, let's look at the next several examples here. For question 59, we just want to evaluate this. Now there's two different ways we could go about this. We could evaluate what's under the radical first. If we did that, we would get -10 squared, which is 100. So then we're going to take the square root of 100, which is just equal to 10. So this is our final answer here. Another way to think about this is that the radical here and the square root essentially undo each other if we're thinking of this in terms of exponents here. And then another way that we can do this, which is actually defined in the book here, it says that if we're taking the square root of something squared here, the radical and exponent undo each other in a sense, and our answer is going to be the absolute value of the number that's under our square here. So the absolute value of -10, which is +10. So that's how we get that here. So there's a couple of different ways to approach a problem like this here. Like I said, this is what they do in the book, so definitely go and check that out. Another way to do it is, like I said, to look at it in terms of exponents. And we're actually going to do that for question 76 here. So we're taking the fourth root of k raised to the 20th power. So thinking about this in terms of exponents, this is the same thing as k raised to the 20th power to the 1/4 power, right? If we're taking the fourth root of something, that's the same thing as raising that thing to the 1/4 power. So using our rules of exponents here, this is actually the same thing as k to the power 20 divided by 4. Right, our exponent rules tell us that we're going to multiply 20 by 1/4, which is the same thing as 20 divided by 4. And evaluating this, we're going to get k to the 5th power. So that's how we would simplify something like this using our exponent rules. All right, so for this last question in section 7.1 here, we're going to look at a word problem. We're told that the threshold weight T for a person is going to be the weight above which the risk of death increases. So threshold weight in pounds for men in this age range is related to their height in inches, and it's given by this formula here. So what we want to do is figure out what height corresponds to a threshold weight of a 260-pound 43-year-old man. So this age falls in this age range, so we're going to use this formula here. So we just want to figure out the height that corresponds to a weight of 216 here. So what we're going to do is we're going to plug 216 directly into this formula here. So doing so, first we want to evaluate the third root of 216 and then multiply it by 12.3. Well, the third root of 216 is 6, so we're just going to multiply that here. So we're going to get 73.8 inches. So that's how we would work a word problem here using our radicals. All right, so in section 7.2 here, we're going to be working with rational exponents. So let's look at this first example here. For question 21, we want to evaluate this exponential expression. We have negative 8 to the 1/3 power. Well, this is the same thing as the third root of negative 8. Now we know the third root of negative 8 is negative 2 here, so this is our final answer for this one. Now for the next one here, question 37, we're going to do something similar, but the first thing we're going to want to do in this case is rewrite this with positive exponents. That's usually always going to be our first step when dealing with negative exponential expressions. So if you remember from a few chapters ago, if we want to rewrite a fraction like this with positive exponents, what we can do is take the reciprocal of this guy raised to the positive 2/3. All right, so that'll be our first step here. Now our second step is what we can do is split up these exponential expressions here. So this is going to be the same thing as 27 divided by 125 raised to the 1/3 power, and then all of this is going to be squared. So this is just using our exponent rules. We know that this is the same thing as 2 times 1/3, which is 2/3 here. So now from here, what we can do is use our exponent property that says if we're taking a fraction to a power here, then each term, the numerator and the denominator, is going to be raised to this power. So this means we're going to be taking 27 to the 1/3 power, which is the same thing as the third root of 27. And similarly, we're going to be taking the third root of 125 here. And this is all still raised to the second power. So this is going to be the same thing as, we're going to have 3/5 here, so taking the third root of these guys, squaring that, so our final answer in this case would be 9/25. All right, so let's look at these next two examples here. In these cases, we want to write each exponential as a radical, and we're going to do so using our exponent rules. The first thing for question 46 here is that we want to recognize that this is saying 8 times x raised to the 3/4 power. So this 3/4 power isn't being applied to our 8 in this case. Now next, let's use our exponent rules and break this guy up. This is the same thing as x cubed raised to the 1/4 power. Now, we know that anything raised to the 1/4 power is the same thing as taking the fourth root of that. So this means we're still going to have our 8 on the outside, but this is going to be the fourth root of x cubed. So this is our answer here, writing this guy as a radical. All right, let's do the same thing for 51 here. Now in this case, we are taking a binomial raised to this fraction here. So this one's a little bit trickier, but all this is saying, using our exponent rules, is that we have this binomial, 2x plus x squared, and this is being raised to the 1/3 power. So we know that anything raised to the 1/3 power is the same thing as taking the third root of that. So we're going to take the third root of this whole thing here. So we're going to have the third root of 2y plus x squared. And so this would be our final answer for this one, writing it as a radical expression. Now, for these next two examples here, what we're going to do is simplify each expression, and we're going to do so relying on our rules for exponents here. So for question 71, we have this term by itself in the numerator, and then we have two exponential expressions here multiplying each other. Now notice that each of these terms here have the same base. So we know that when we are multiplying exponential expressions with the same base, what we can do then is add their exponents. So we're going to keep the numerator as is. Nothing's multiplying this guy here. But in the denominator, we're going to have k raised to the 2/3 power plus a -1, so -1. So this is going to be the same thing. We have k raised to the 1/3 power here, and then 2/3 minus 1 is going to give us -1/3. So we're going to have -1/3 in our denominator. Now another exponential rule says that if we are dividing two exponential expressions here that have the same base, we can subtract their exponents. So this is going to be the same thing as k to the 1/3 power minus negative 1/3. Since we're subtracting a negative, we're going to add these guys. And our final answer is going to be k raised to the 2/3 power. Now, if we were to write this as a radical, this would be the same thing here as the third root of k squared. Either answer is correct though. Now, this next example here is a little trickier, but again, let's zoom in a little bit. Again, we have this expression raised to negative exponents. So the first thing that we're going to want to do is rewrite this guy with positive exponents. And just like we saw in a few examples ago, we can do that by taking the reciprocal of this guy raised to the positive exponent here. So this will be x to the negative 4 times y to the 1/2 power over x raised to the 8 and then y to the minus 8 power. This is all being raised to the now positive 2/3 power here. So now from here, let's apply some exponent rules. We know that if we're taking this guy raised to 2/3 here, this 2/3 is going to be applied to both of these exponential expressions here. So we're going to have x to the negative 4th raised to the 2/3 power times y to the 1/2 raised to the 2/3 power, and that'll be in the numerator. And in the denominator, we're going to have the same thing, this 2/3 applying to both of these guys here. So we're going to have x to the 8th power raised to the 2/3 times y to the negative 8 raised to the 2/3 power. All right, so from here we can multiply these guys using our exponent rules. For this first guy here, we're going to have x raised to the negative 4 times 2/3. So multiplying this guy, we're going to get x to the negative 8/3. Similarly, for our y, we're going to end up with y to the 1/3 power in our numerator. In our denominator here, we're going to have x to the 16/3 and then y to the negative 16/3. All right, so we're not done yet though. We still have negative exponents. So what we're going to do is bring this guy to the top and write it with positive exponents, and then this guy's going to go to the bottom here. So we're going to end up with, running out of room here, we're going to have y to the 1/3 times y to the positive 16/3, and in the bottom we still have x raised to the 16/3 power, and then we're going to bring down this x raised to the 8/3 power. Now from here, notice in the numerator we have the same base for these two guys, so that means we can add their exponents. So our final answer in the numerator, we're going to have y raised to the 17/3 power, and in the denominator here, we're going to have x to the, we're going to end up with 16 plus 8, so that'll give us 24 divided by 3. So that'll give us x raised to the 8th power here. Okay, so just emphasizing this guy here is going to end up being x to the 24/3 power. All right, so that's how we get x to the 8th power. So this is going to be our final answer for this case. All right, and for the last 4 examples in this section here, we're going to write each radical as an exponential and simplify. And we're going to do so relying heavily on our exponent rules again. So let's look at question 57 here. We have the third root of 4 to the 9th power here. So we could evaluate this as 4 to the 9th and then take the third root of that. But using our exponent rules, we know that these two guys here are equal to each other. Then what we can also do is multiply this 9 times this 1/3 here. This gives us 4 raised to the 9/3 power, which is the same thing as 4 cubed, which is the same thing as 64. So that's how we can use our exponential rules to write this as an exponential and simplify. So let's look at this next example here, 93. Now in this case here, let's rewrite each of these guys here as an exponential first. So we have x cubed raised to the 1/5 power times x raised to the 1/4 power. Now this first guy here, we can just multiply these guys. So this is going to give us x to the 3/5 power times x to the 1/4 power. Now we're multiplying these two guys and they have the same base here. So that means again, we can just add these exponents. So what we're doing is we're taking x to the 3/5 power plus 1 over 4 here. Now getting a common denominator here, this is going to end up being, let's just do every step here. This is going to end up being x to the 12 over 20 plus 5 over 20 here. So just getting a common denominator for these two guys. So this is going to end up being x raised to the 17 over 20 power. We can't simplify that any further, so this will be our final answer. All right, let's look at this next example, 96 here. So again, the first thing we're going to do is rewrite both of these guys in the numerator and denominator as an exponential. So in the numerator here, this is the same thing as w cubed raised to the 1/4 power. And in the denominator, this is w raised to the 1/6 power. Next, let's multiply the exponents in our numerator. This is going to be w to the 3/4 power. Now again, in our numerator and denominator, these guys have the same base. So what we can do, since we're dividing these guys, is subtract their exponents. So this is the same thing as w raised to the 3/4 power minus 1 over 6. Now getting a common denominator here, this would end up being 18 over 24 minus 4 over 24. So we're going to end up with w raised to the 14 over 24, and then we can simplify that a little further. This will be the same thing as w raised to the 17 over 12 power. So this is our final answer for 96. And then lastly, let's look at 101 here. This one's a little funkier. We have the 4th root of the 3rd root of m. But again, let's just use our exponent rules here. So the first thing we'll do is write this radical as an exponential. So this is the same thing as the 3rd root of m raised to the 1/4 power. Now inside our parentheses here, this is the same thing as m raised to the 1/3 power. So that is our expression written as an exponential, but we also know that we can multiply these guys here. So our final answer here would just be m raised to the 1/12 power. All right, so this brings us to section 7.3 here. So in this section, we're going to work on simplifying radicals. We're also going to look at the distant formula and graphing circles. So first, let's start with multiplying the radical expressions here. And to do that, we're going to use what's called the product rule for radicals. Now that is listed in the textbook, but I also wrote it down here. And what it says essentially is the product of two nth roots is going to be the nth root of that product here. So let's look at question 17 here. We're multiplying two square root expressions here. So since we have the same square root, what we can do is just multiply these guys. So we're going to have 14 times 3, which will give us 42, and we still have p, q, and r, and this is all going to be under our square root. So that's our final answer for that one. Let's look at 26. Here we're multiplying to 4th roots, so that means we can just multiply everything under these radicals here. So we're going to multiply first 3 times 6, so that'll give us 18. Then we have y squared times y, so these guys we can multiply them and we're going to get y cubed, and then we still have this z here, and this is all under the 4th root. So that would be our final answer for that one using our product rule. All right, so let's look at the next several questions here. We want to now simplify these radical expressions. So for this one here, what we're going to do is split up the radical in the numerator and the denominator. So what I mean is, this is the same thing as taking the 4th root of 81 over the 4th root of x raised to the 4th power. So we still have this negative on the outside. If we take the 4th root of 81, this is going to give us 3. And if we take the 4th root of x raised to the 4th power, again, these guys are going to undo each other. If you think about it in terms of exponents, this is x raised to the 4th, and this whole thing is being raised to the 1 over 4 power. So multiplying those guys, we're just going to get x by itself. We can also use the rule that when these guys are the same, our final answer is going to be the absolute value of the guy on the inside of our radical. So this is going to be negative 3 over x. Let's look at this next question here, 58. We're taking the 3rd root of 24. Now, 24 isn't a perfect cube, But what we can do is split 24 up into its factors. So this is the same thing as the third root of 8 times 3. Now what we can do using our product rules, we can split up these two products here. We can look at this as the third root of 8 times the third root of 3. Now the third root of 8 is going to be 2, and we can't simplify the third root of 3, so we're just going to leave that as is. This is going to be our final answer here. So whenever we're simplifying radicals like this here, it is good to try to break up our answer under, or a number under our radical, into the factors that we know will be perfect cubes or perfect squares and so on. So this brings us to question 74 here. So we're going to do the same thing, but it is a little trickier. The first thing that I'm going to do, since we're looking at a square root, is I'm going to try to break everything up into factors that are perfect squares if possible. So first, we know 169 is a perfect square, so we're going to leave that as is there. That's going to be 13. But here we have s raised to the 5th power. So this is going to be the same thing as s raised to the 4th power times s. And the reason why I'm picking to the 4th power here is because I know that 4 is a perfect square. Similarly, I have t raised to the 10th power. We're breaking this up into its factors. This is going to be t raised to the 4th times t raised to the 4th times t squared. And I'm picking these guys because these guys are going to be perfect squares here. Now, remember the exponent rules here. When we're multiplying these guys with the same base, we are adding their exponents. So these three together are the factors of t raised to the 10th power. Now, this is all under our radical. So let's do this step by step here. Using our product rule for radicals, we know that if we're taking the product of all these guys under the square root, this is the same thing as the square root of all of these guys. Okay, so just using our product rule here, this guy. So after breaking that up here, we can evaluate this. We know that the square root of 169 is 13. Now the square root of s raised to the 4th power is going to be s squared. Then we still have the square root of s here because we can't simplify this any further. Then the square root of t to the 4th power is going to be t squared, and so we have 2 of those. And then we know that the square root and this square here is going to cancel each other out, so we have one more t there. So let's simplify this a little bit further. This is going to be 13s squared times t raised to the 5th power times the square root of s. And so this is going to be our final answer here. Let's look at this next example here, 116. We're again going to use our exponent rules here. We're multiplying these guys. In this case, we're not going to use our product rule because we don't have the same root here. We have the third root and the 4th root, so we can't multiply these guys under our radical. But like I said, we can use our exponent rules. This is y raised to the 1/3 times y raised to the 1/4 power. So we know that we're going to add these guys together since we have the same base of y. Doing that, we're going to get a common denominator of 12, and then adding those guys together, this is going to be y raised to the 7/12 power. And so that would be our final answer for that one. Alright, so in these last examples here, we're switching gears a little bit. We're going to be looking at the Pythagorean theorem, our distance formula, and graphing a circle. So let's look at this first example here. We want to find the length of the unknown side C for this triangle here. Well, we're going to use our Pythagorean theorem. It says that a squared plus b squared is going to equal to c squared when we have this right triangle here. So we can solve for this unknown side by plugging in our values for a squared and b squared. So we're going to end up with 3 squared plus 4 squared is equal to c squared here. So we know this is going to be 9 plus 16 gives us c squared, and let's move over here. 9 plus 16 is 25, so this tells us c squared is equal to 25. So if we want to find c, we're going to take the square root of both sides, since we know that if we take the square root of a square, we're going to end up with just what's under our radical here. And we know the square root of 25 is 5, so this tells us that c is going to be equal to 5. So the length of this unknown side here is 5. All right, let's look at this next example here where we're going to be finding the distance between a pair of points. So I've written down our distance formula here. We want to find the distance between a pair of 2 points here. We're going to take the square root of this under our radical here. So all we have to do in this case is identify. So this would be x1 and y1, and this would be x2 and y2. And so we're just going to plug these values into our distance formula. Let's move this down a little bit. So our distance then is going to be the square root of x2 minus x1. So this will be 3 minus negative 6. So this will be 3 plus 6 squared. And then we're adding the difference between y2 and y1. So this will be negative 4 minus 5 squared. And this is all under our square root. All right, so all we have to do is simplify this. We're going to end up with 9 squared plus a negative 9 squared. Now we know 9 squared is going to give us 81, and negative 9 squared will also give us a positive 81. So we're going to have 81 plus 81 under our square root, which is the square root of 162. And so this would be our final answer here for the distance between these 2 points. All right, so for this next example here, we want to find the equation of a circle that satisfies these 2 requirements here. So if you go back to the textbook, you'll see that a circle is defined as the set of all points on a plane that lie a certain distance from a fixed point. Now that fixed point is going to be the center, and then that distance is going to be the radius of our circle. So since we're looking at a fixed distance from a fixed point, we're going to use our distance formula here. So again, that distance from the center is going to be our radius. So that's going to be our distance, d here in our formula. And then the center is going to be a fixed point. So that's going to be this x1 and y1 coordinate here. So what we can do is plug in this information into our distance formula. We know that our radius is going to be 2, so I'm just going to plug in 2 for d. This is going to be equal to, we're going to have x minus our x coordinate for our radius. So this will be minus a negative 4. So this will be x plus 4 here. Then for this next term here, we're going to have y minus our y coordinate. So that'll be y minus 3 squared. And this is all under our square root. Now, when we're writing the equation for our circle, we could leave it like this, but we generally like to write it with our exponents versus our radical here. So what we can do to get rid of this radical is we can square both sides of our equation here. So we're going to end up with 4 is equal to x plus 4 squared plus y minus 3 squared. When we took the square root, we got rid of this radical, so we're just left with everything underneath our radical. So this would be our equation here for a circle that satisfies this here. All right, so for our last question in this section here, we're now given the equation for our circle and we want to graph it. So the first thing we're going to want to do is identify the center and the radius. So notice that our equation is of this form here, so we don't have our square root. So in this case, this radius here has been squared. So that means the radius is actually going to be the square root of 9, which is 3. Okay? And then our center is going to be the fixed point. Our x-coordinate is going to be this here. Now remember the formula says it's going to be x minus our x-coordinate. So the only way that this could be positive is if our x-coordinate is also negative. All right, and then our y-coordinate is going to be positive 2, since in our formula this guy is going to be y minus the y-coordinate. All right, so from here we can graph this. The center is negative 3, 2. So that's the first thing we're going to be plotting. So that'll be our center here. Now everything else is a fixed distance away from this point, and that distance is 3. So let's go 3 units in every direction here. So I'm going to go up 1, 2, 3. So this will be another point on our circle. Now then I'm going to go 1, 2, 3 to the right of this guy, to the left, and then down here. So from here, we can kind of just do a rough sketch of our circle. It'll look something like this here. And then if you're on an iPad like I am, it'll make that circle much nicer. So that'll be the rough sketch of our circle with this equation here. All right, so this brings us to 7.4, which is the last section in this video. We're going to be adding and subtracting radical expressions. So we're going to do so using our distributive property here that says that a times c plus b times c is the same thing as a plus b times c, right? So this c here is being distributed to both of these terms here. All right, so let's look at our first example, question 12 here. Now, we want to subtract these two guys here. But notice we have the square root of 32 and the square root of 8. So using our distributive property, if these square roots were the same, we could pull them out and then just take the sum of the numbers in front of our square roots here. But these guys aren't the same. So what we're going to try to do is try to rewrite maybe this square root here to look like this one. Now we can do so using the fact that 32 is the same thing as 8 times 4. So, let's write over here. Let's break up this first term here. 4 times the square root of 32 is going to be the same thing as 4 times the square root of 8 times 4, which we could also write as the square root of 4 times 2. That'll give us 8 times 4. So this is our factors of 32 broken up here. Now doing the same thing for our second term, this would be 2 times the square root of 4 times 2. All right, so using our product rule for these radicals that we saw in the last section, this is the same thing as 4 times the square root of 4 times the square root of 2 times the square root of 4. And then similarly for our second term here, breaking these guys up. Now you don't have to break it up step by step just like this here. I'm just emphasizing what we're doing, showing each step so we can follow along. So from here, we have the square root of 4 and the square root of 4 here. So we know that these are both 2. So we're going to end up with 4 times 2 times 2 times the square root of 2. And similarly for our second term here, we have 2 times the square root of 4, which is 2 times root 2. So let's simplify this. We have 4 times 4, so 16 root 2 minus 4 root 2. Now notice that both of these terms here are being multiplied by root 2, so this tells us we can use our distributive property here. We can pull out this root 2 from both of these terms here. So we're going to have 16 minus 4 times square root of 2, which is going to be the same thing as 12 times the square root of 2. And so we can't simplify that any further. This would be our final answer. All right, let's look at a similar example here. Now we're subtracting 3 terms, but we're going to use the same process here. So we know 54 is going to be 6 times 9. 24 is 6 times 4. And 96 here is the same thing as 6 times 16. Now, there are different factors of 54, 24, and 96, of course. We can break all of these guys up into smaller factors. But let's start with this for now. We can rewrite this first term here. We have 5 times the square root of 6 times the square root of 9. Now, it might make some more sense why I left it as these factors here, because the square root of 9 is going to be 3. 9 is a perfect square here. So is 4, and so is 16. So let's do the same thing for this second term here and our last term. We don't have to do it this way. Again, we could have broken each of these guys up into smaller factors if we'd like. We'll end up with the same answer. But doing it this way here, our first term is going to be 5 times 3 times the square root of 6 minus 2 times 2 times root 6 minus 2 times 4 times the square root of 6. Now, what we can do is multiply these guys here, and then notice that each of these guys has a root 6 term in them. So we can use our distributive property and pull them out. So let's multiply these guys first, though. Now, pulling out our root 6, we're going to end up with this here. Now, subtracting these guys, we're just going to end up with 3 times the square root of 6. So as you do these problems more and more, you'll see why you want to pick certain factors like this. I picked these guys here because 9, 4, and 16 again are all perfect squares, and then I know I'd be left with a root 6 for each of these terms here, which I could easily pull out. Okay, so just take some practice to get used to recognizing what to do here. All right, so for this next example here, we're adding these two radical expressions here. We're looking at the third root for both of these as well. Now, for each of these guys, we can actually simplify this a little bit further. So that's what we're going to do first before we try to add these guys together. So for this first term here, we're looking at the third root of 64 times the third root of x times the third root of y squared. And then for the second term, third root of 27 times the third root x raised to the fourth power times the third root of y raised to the fifth power. So from here, let's simplify this. The third root of 64 is going to give us 4. Now the third root of x and the third root of y squared actually can't be simplified any further, so let's put them back under the same radical. This will be x times y squared. Now for our second term here, we have the third root of 27. This is going to give us 3. And we also have the third root of x raised to the fourth power. Well, actually, we could break this guy up into two factors. This is the same thing as x cubed times x. So we can break those guys up into the product of two radicals here. And then same thing for this third guy here. We have y raised to the fifth, or the third root of y raised to the fifth power. So we can rewrite this as the third root of y cubed times the third root of y squared. All right, so this is going to be the same thing. Our first term here can't be simplified any further. But for our second term here, we still have this 3 out front, but then we have the third root of x cubed. That's just going to give us an x here. Then we also have, so we're just looking at this term and this term, because we have the third root of y cubed. So this is just going to give us y. The third root and the cube are going to cancel. And then we're still left with these two guys here. These guys can't be simplified any further, so we're going to put them back under the same radical here. All right, so in this case here, we just broke these guys up into factors that we knew would simplify further. All right, now for both of these terms here, we do have the third root of xy squared, so we can pull that out. We're going to be left with 4 plus 3xy times the third root of xy squared. Now from here, we can't simplify this any further. 4 and 3 times xy are not like terms, so we can't combine them. So this would be our final answer. And in fact, this first line here could also be considered our final answer. All right, so let's look at our last example here. Question 64. We're going to be adding these two radical expressions here. Now, just like in the last example we saw, we can actually simplify these guys a little further. So let's do that here. We have this minus 4 out front, and for this first guy here, we're taking the third root of 4, and then the third root of t raised to the 9th power. Now, actually, what I'm going to do in this case, actually, no, let's do this step by step here. So for this next guy here, we have the third root of 9, and then the third root of 12. All right, so this radical here applies to both guys, our numerator and denominator, in both of these fractions here. Now from here, what I'm going to do is I'm going to break up our t's here in both of these denominators so that we can simplify them with the third root here. So I'm going to break them up into their factors. For this first guy here, we're multiplying negative 4 times this whole thing, so I could rewrite this as negative 4 times the third root of 4 in our numerator. Then in our denominator here, we're looking at the third root of t raised to the ninth power. So this would be the same thing as the third root of t cubed times t cubed times t cubed. Right, when we're breaking these guys up into their factors here, we're going to get this because we know that when we multiply exponents that have the same base, we're just going to add their exponents here. Now, similarly for this second term here, I'm going to do 3 times the third root of 9, bringing that to the numerator. And in the denominator here, I'm going to end up with this here, which is the same thing as t raised to the 12th power, and we're taking the third root of that. Now we know we can break this up by taking the third root of t cubed and the third root of t cubed and so on. Doing that, we're going to end up with the third root of t cubed, which gives us t. Third root of t cubed also gives us t, and then the third root of t cubed gives us another t. So evaluating this in total, we're just going to get t cubed in our denominator here. Now for our second term here, we're going to have the same thing. These guys are all going to cancel with our third root here. So I'm going to end up with t raised to the 4th power. Now from here, we can actually add these guys. We can get a common denominator. So let's do that here. In order to get a common denominator, we'll multiply this first term by t over t, so that we end up with t to the 4th power in both denominators here. So our first term becomes this here. Now we can add these guys. We're going to end up with minus 4t times the 4th root of 4 plus 3 times the third root of 9 all over our common denominator of t raised to the 4th power. Now we can't simplify this any further. We do have, actually this should be the third root here. We do have the third root of both of these guys, but these guys aren't the same number. We're not going to be able to pull anything out here. So we can't simplify this any further. This would be our final answer for this one. All right, so that'll be it for this video.